the mute. Can you hear me properly? Thank you all for being here.
Yes, thank you very much for being here. And I would like to thank David Barroso for having encouraged me to come over here, and also to Roman. So without further ado, I'd like to tell you a story which is not very frequent or very common. And well, I've been working in technical security up until 2005. And then later on, I move on to something else. So let us say that I didn't devote my career to that. So as I say, today we will be talking about chips. Everyone has a chip, and actually I believe this is the most widely spread component in the world, because nowadays all devices have a chip in them, and actually they are the latest frontier in terms of security. With this I mean that if in the design then you connect a bit or you do a complicated design that is weak, if you have a weak design, well, there is no way back. We are talking about physical elements. Once they are built, you cannot go back to them, you cannot recombine them. So they are a huge challenge, and to me this is a hobby, and well, I would tell you why it is a hobby to me, and I learn a lot. So there are many things that, well, at the end of the day, I end up seeing things that are not related to software. The mindset is completely different. I guess that those of you that have gone to university, you have an engineering degree, you have touched upon these things. I'm not an electrical engineer either, but I want to say that this is very important, because if I manage to do this, I am sure that you all can do it as well. Well, the only need to be is just to be very perseverant, okay? You have to persevere, you have to work hard on that. And I believe that all of you, one of the characteristics that you share is just looking for things all the time and being really stubborn. And it's really good fun, and then it is kind of very much different to what you are aware of. So now I'd like to discuss a number of things to you today, and as I say, I am coming from area that I'm not very much well aware of electricity, but still I would like to give you a brief introduction as to how these chips are being manufactured, because if you really want to dismount them, you really need to know at least how they are manufactured to understand the logic of it. Later on we will talk about decapsulating, microscopy and deep processing. Then we will move on to inverse engineering, simulation, and then I'll share with you a practical case. And also something related to what I mentioned before. This is a hobby for me, and this comes from the arcade world. So a year ago I started to collect games from when I was small, and then I found that it was very interesting, to go back to arcade games, and this comes from arcade games. We are talking, has software component, but primarily this is physical, this is hardware. All this comes from transistor, from radio. In 1947, Dell built the first transistor, the practical one, so meaning that the one that works. In the past, all these had been patented, and actually this was built whenever the patent that was issued 20 years ago expired. And that's where the revolution started. The revolution that we have up until nowadays, and the revolution that has made us to come to where we are today and to be giving this presentation. So most of us were born after this the year when this was manufactured, and then actually this won the Nobel Prize years ago later on. So, and at the end of the day, this is a tap or a switch or an amplifier. So, well, it is just a tap. It's either open it or I close it. I let the fluid go on or not, okay? Some of them do it in the reverse manner, and sometimes they do it in the straight manner. So actually the milestones that have taken us where we are today are the following ones. So we have the first patents back in the 40s where this was introduced, and then the thing that gave rise to the revolution that we have today is the CMOS that you are all aware of, and thanks to the CMOS technology, the technology industry is where it is. Then we also have the new technologies that are also being used, for instance, by Intel to move on or to go as far as possible in terms of integration. So this is a MOSFET. This is the transistor that we all had up until a few years ago. I'm not going to dwell too much on that, but just let me tell you that this is a side view, this is a cut, and then we have different layers. This is very important for what we will be doing right now. As you know, this is lithography, so we do a sequential building, bottom up, with very many other processes. The integration level of these things is just spectacular, and as far as I know, this is highly impressive for me. So in the second column, we see the levels of integration of transistors. Now we have like 3 billion. So Intel announced the other day the new consumer processors. They have 3 billion transistors in them. And of course, it has to be designed, supported, of course, by software. Many of the current tasks are automatic, and it is just impressive. We are shifting from hundreds of thousands to billions. And before we move on, so this last but one column is very important because it tells us about the process of integration. In all the families, in all the generations, you have the whole industry working about new standards, new processes of definition of construction and manufacturing, and also on the machines or equipment that are needed to build those chips. They are working, as I say, in families by in generations. Okay, so these things are built in huge facilities. They are kind of like car manufacturing facilities. They are just giants. And unfortunately, many liters of chemical products are being used in these facilities. When we watch that in a video, we find, well, we always see like clean people because these places, these facilities are cleaner than some hospitals or some operation theaters, but they are extremely polluting. So this is a service piece, and at the end of the day, this comes out of sand. This is an ingot. And basically, this is cut number of discs, as you have seen in videos before. And then on top of those discs, a story is built. And that story is a very complicated process of manufacturing, following very sophisticated technology. You know that there is the industry fully devoted to that. And just let me tell you that these processes are kind of like Lego, where you are adding different layers, photomasking, lithography, etc., to end up with the number of features that are produced or manufactured on top of that disk. At the end of the day, we are talking about 400 or 500 chemical processes. Many chemical substances are involved in each of these chemical processes, and all this is being recycled later on at the end of the cycle, but it is also highly polluting. So that's one of the downsides of it. So at the end of the day, we end up with something like this. At the bottom, we get to see these transistors. Then on top of that, we have all those layers from M1 to M28. These are the interconnections. These are the O2 ways. This allows us to transfer very complex signals, and these layers could be more than that, not only 8 as we see here. So this is what I'd like you to remember. This will be a 3D representation of what happens down below. Okay, we see the disk at the bottom, then in pink we have the transistors, the polysilicon, that is used to create them, and then the metal layers. Do not take that this is a very weak figure, something that if you blow to it you will destroy it or dismantle it. They are solidified, they are really solid and robust. And as I said before, each disc has an integration of N chips. The higher the number of chips that we can introduce, the better for the manufacturers. And then once you have built this comes out of the machines, then they undergo visual inspection, then they really verify whether the chip passes or not. As I say, optical inspection, visual inspection. They also do electrical inspection sometimes to check the different contacts in it. And also very surprising, at the end of the day, this is cut with a disc, with one of those saws that sometimes are used to cut ceramics or wood. I don't know how they do it, but they just do it. It is just so impressive to see how these precise or accurate cuts is being made, and then on top of that it is put on the top of the containers, and then do this bonding, these connections. This is being made by a machine at a very high speed. It is really impressive to see this bonding wire. This is kind of like a welder that is kind of expelling out gold. And then we see here a bridge between this small world and this big world, and contact is being made on the chips. And then we have the encapsulation. You are all aware of encapsulation. And to finish with this presentation, we have an N number of manufacturers. This is a representation of what they like to do. So if you look at the chips inside, you get to see even like Easter eggs. So basically the logotypes represent the pixels, and they are a bit of artists. And actually, building or manufacturing or designing a chip is an art. It is also a science. So here we see the encapsulations. In the past, I don't know whether you remember, the first one, the dip, was very typical. It was very typical, the one that existed for many years the dual one. And now we have the S-SOPs, the T-SOPs. They are more and more sophisticated. Then we also have like more legs and thicker legs as well as more sophisticated materials. So decapsulation, microscopy, and deep processing. Now we know how it works, or at least we know how they are manufactured, and now we want to go backwards. So warning. So take this very seriously. And to open up these chips, okay, you really need to use acids. Some acids are very dangerous. All of them are dangerous. Some of them are very dangerous. I didn't really want to use or to show any images. If you don't use these properly, if you don't use your ventilation hood, your protection equipment, and the right ventilation, you could be in deep trouble. If you know any chemist or any physicist, please ask advice from them. As I say, careful with the using of this acid, and these acids are necessary. Okay, and this is what we want to achieve. Okay, this would be the perfect thing for us to do. That is to say, opening a chip which is functional. We have side view of this chip, which is the traditional chip in the industry. This is the DIP, and then we have the support of the chip with the bonding wires. These are mainly made of gold, and they are directly connected to the legs. If you want to have a living sample of the chip, you want to keep the legs. So this is the clean way to do it. I'll tell you the two ways to do it. Then microscopy. If you don't have a microscopy, you wouldn't be able to do anything. That's the first thing that you need. You need metallurgy 1, okay, and the one that is used in the steel making industry. And then it should also have specific tray or plate. And also very important, this is a 2D visual. For us to do inverse engineering and to do it right, that is to say, the one that allows us to achieve our objective, we want to deprocess what was processed before. So we need to deconstruct the chip. You remember that there are some interconnecting plates and other polysilicon plates. So if you don't know what is the relationship between the different layers, you will never make it to your destination. Down below, things are huge and are very many of them. So unless you have lots of practice, lots of intuition, you will not get it right. And the higher the number of views of the layers, the better. This is what the industry knows as the full metal. This is fully made of metal. If you look at it in the microscope, this is what you will see. So this is a technology probably from early 90s. And then you see a metal layer on top and another metal layer below, and then the polysilicon layer. So these are 3 examples of the 3 different sections that you find in the chip. And if you don't have these 3 views, unless you have lots of curiosity, you will never achieve your objective unless you are talking about something easy to attack. In terms of decapsulating types of decapsulating, we have the destructive one, where you keep the functional chip, and the live one. And, well, if you destroy it, it's not a problem unless it is the only one left in the world. And to destroy the chip, there is a basic team. So that is to say, coats, gloves, pipes, tubes, goggles. That is to say, the usual protection equipment. Also a heating base for the acid to get to the right temperature, and extracting a hood or just work in the open air. And then also nitric acid, minimum 70%, and then heat it up to at least 90 degrees. There is lots of information on the internet. 70% minimum, ideally 90%. It's difficult to achieve the 90% one. Actually, the 90% one, I saw it on salt in Italy. Below 90%, you require the heating base, and then the chemical that will help you, acetone, neutralize the acid. First of all, we want to do preparation. We want to open a cavity in the chip. We don't really want to touch the island or the bonding wire. Amateur, Dremel. Lots of patience and testing. The professional, for professional, you use machining. I don't know how you say that in Spanish, but basically these are machines, equipment that do sections. They do sections. They are kind of drilling machines. And then, well, in the labs, most of the times they use laser. Very professional, they remove some of the millimeters. They just create this cavity, and that lets the acid filtrate. And then when you have a cavity, you put the acid in it, and then just to wait up until the reactive agent stays in place. And then if the cavity is flat enough, then the penetration will be clean one. And then if you insert on the acid, heating base, then chip inside, and when you think you're ready, you have to take it out. Careful, careful. Okay, this is full of acid, and you careful with it. And then the pro attack without reaching to the lab. This is, well, you can use these machines. They go through the full cycle. They have the acid, they have the heating system, and they also have the neutralizing system. So whatever comes out, I don't know whether you can see it or not. Well, do not try it. Okay, so this is a combined process. At the end of the day, there will be a decapping of the chip. The machine will do that for you. And then, well, this is the lab image. I've never seen machines of this kind myself. This is a feed, and this is the most advanced technique that labs use. This is a ion cannons, and it eliminates the layers of the materials, and as it does so, it also does some scanning. It takes advantage of the rebounding of the signals, so it does scanning and destroys the elements simultaneously. You deconstruct all the layers, the same as the TC scan in humans, but this one is more destructive and it uses metallurgical elements. Microscopy, very important. If you cannot really see what's underneath, okay, you will not get anywhere. And then amateur amateur, yes, you can get a very plain microscopy and get what you get on the left. Well, if you're talking about something very old that doesn't really make lots of sense, well, as you can see on the screen, but out of experience, well, little by little you get used to seeing that, and you're going to say, oh yeah, well, it is like that. But if you really want to reach or to see technology brightly and clearly, as we can see on the right, well, this is what the practical case that I wanted to share with you. This is at 88%, and I didn't even use the best possible microscope. Then to go below and to reach as far as that and to see all the layers, you need a good microscopy that is like $3,000 or $4,000 and many hours in the lab. Well, however, if the microscopy is not has such a high quality, you can get one for $100, and then a lab can also do that for you. Okay, so don't you think that you can get like Intel Core 2 and then to add 2 drops of acid to it and see what happens to it? What I mean is that this has advanced a lot, and all the technology, all the integration that is being currently now is below the optical spectrum. And unless you have a very electron microscope, you need lots of patience to scan all the areas. If not, you will not get it. And then the processing of the layers is also time consuming. What are the advantages? What can we support ourselves on? In a concept, often safety chips are not made with the latest technologies. They are not customs, as it is said in the industry, because no one will just produce millions and millions of chips, safety chip using the latest technology. That is for Intel, for AMD, for the big leaders in the industry. Often what we find in safety chips, and there is a small group of people or a group of people in the world that do this as amateurs, well, you see that they use, or you find that they use technologies from the 90s, affordable technologies. So microscopy in itself requires automation. It is not only quality and power, but it should also you should also be able to automate it. And the good microscope have a tray which is known as XY, and then it moves with lots of accuracy. So for you to understand this, I had a chip here, the one that we used for our study. So this is like a nail. So notice the size, and notice this photograph. Notice everything that we have inside, and this is a sequence of images that have been attached to united to each other. Unfortunately, there are tools and people with time to work on that managed to build this. Silicon Chrome, this is one of the largest libraries about that. You can get lots of information about these tools, the tools that Mr. McMaster, who is one of the best experts, the great experts in the world of reverse engineering, has compiled. So once you have the material that you need visually, what you have to do is to do the graphical editing. So you have to take your favorite tool and then from there, well, start to do things. Well, for instance, tracing if you find the signal, and then with patience you will get all these cables, these pistes, little by little, and you will trace them. There are no automatic tools. Well, I think there was a German engineer who had developed a software, but the software didn't work. I tried it myself. I also discussed it with other amateurs. No one is using that software made by the German. So lots of the work that requires lots of time, and then the processing, which is, I believe, the most important part. You really need to get to the different layers. See how you do that. Amateur method, trial and error, lots of patience, lots of experimenting, lapping. This is, well, basically you do that by doing sanding. You take your small piece and then part, and then you try to cut it, or at least you try to reduce the sample in millimeters or less than millimeters. You do that with lots of patience. You go back to the microscope over and over again up until you find out whether you have reached all the layers. Well, it is full of failures and everything, and flaws, everything you can think of. Often you do that with an acid that eats up all the top layers, the metallic layers, which is the hydrofluoric acid. This is extremely dangerous. It is one of the big things you should be really afraid of. It will eat up your bones, your skin, your everything, crystal, glass, everything. As I say, careful. In the lab, we scan the sample as you do the FIB-RIA. Okay, now software, reverse engineering and simulation. This is, well, magic. This is a free tool which is used to design chips. Okay, it is free. You can download it and it runs in Linux. You can do something as simple as that, which is an inverter. I'll show you how it works, or a full chip. For instance, a chip with millions of transistors. You could do that, and to me, this is the basis of everything. Thanks to that, we can do this, make this reverse engineering effective. We can reproduce what we see, what we feel, and then to validate it electrically. Cadence is a software, same as Photoshop for pics, for pictures, and Pro Tools for music. Electric validation, which is very important. Well, if we do all these designs and all that, but we cannot validate them if we are not electrical experts, that's the only thing that we can do. In the free world or in the amateur world, we have tools such as IRSIM that allow us to validate models electrically and to do reverse engineering. In this case, I left the test open so that you see the commands, the connection of the wires, the cables. I changed the entries, and you see this is an inverter. I inserted a high input, and then the exit, I put it at the bottom. So IRSIM. Then after you open them, you take a picture of them, and to process them and work on the different layers, you will support everything on that. This is an example of the process. This is a photograph of a component. You analyze it, you study it, then you wonder what it does. Then you process it, you have the different layers, and then we achieve a simulation that we verify electrically. This is an XOR. I'm sure that you all know it, and well, that's about it, not much more than that. And as I say, lots of hours and, well, intuition and learning as you do it. This is trial and error, nothing different to what you do now. And now, practical case, arcade world. I started to collect things and I ended up in this. I found that in the arcade world there are many games that are protected. In this case we are talking about a chip known as Kabuki, which is a Z80, and this Z80 has a customization that has been made on top and has crypto in it. It has ciphering functions on it. And then you find games such as Punk. I'm sure that you know it, same as Cadillac Dinosaurs. They are classic games. And what happens here is that after some time, when this battery dies, the game dies with it. And this is so because the memories that have been inserted are ciphered, and only the processor inside is aware of the deciphering keys. And as the battery is alive, they are inside, but then when they die, the game is over. Blue screen or whatever color screen, and then it dies. Why did they do that? Because of the copies. Well, this was the largest industry in that time, larger than Hollywood filming industry. It moved billions and billions and billions of dollars in the world. I'm sure you spent lots of money on those machines. I'm sure I'm not the only one in here. We found that there was a counter industry that did copying and copying and copying. And if you are collectors of this, you know this much better than me. And especially in Spain. In Spain, the only thing that you find are copies on XOR, and you don't find the originals. And then the need arose, and the arcade industry went into security and ended up ciphering games and inserting custom chips. You know, well, imagine how difficult it is to build a chip and to customize it, and only these big companies, really successful company, managed to invest so much money, but still, well, they couldn't really put a stop to so much copying that lasted for many years. Well, the first time that I got a system, I bought a signal analyzer, and I started to understand what happened when the CPU died, when the battery was lost. I even decided to do a hello world in MAME to understand my hypothesis. My hypothesis is whenever the CPU runs out of battery, the ciphering keys go to 0, because the memory, considering the registry, well, the industry was saying, well, it sets to 0, and then ciphering keys, they also go to 0, yes, but they were null or 0, but with an unpleasant surprise. This is an execution sequence, 2 branches, encrypted and ciphered, and this not cipher encrypted. Yes, the keys were 0. Programs were executed, but the memory readings were also decrypted. So then the CPU, the memory, what was clean when tried to read it, the CPU used to decipher it, to decrypt it again. So any program that uses a memory does not run it, does not execute it. Instead of go to 5B, it goes to 8D. And this is all because it has deciphered it and it hadn't executed. So the next one, because I'm very stubborn, I decided to discover what happened with this, well, happens in reverse engineering, months and months, patience, and then people around me helped me, well, open it. And this is what I found. This is the actual processor. These are the different, well, FCLC, Kabuki, which is the safety chip, VTI, which is the company that did it, and then it was done back in the 87. So, and then what's inside? Well, we have a core C8 one in blue, and then customs for this ciphering. And then inside that, we can identify many things. Well, in bus interceptions, to do that man in the middle, they are doing the man in the middle of a part that works, which is in the industry. Then memory for these encryption keys and other configurations, and then, well, a number of networks that decipher according to the design. Well, I didn't break the design of the CPU or of this system. It was already cracked through analysis, understand mathematical analysis at the end of the 90s, and then that was integrated and taken in by the MAME team later on. So I tried to understand how these chips were programmed. If I had an original hardware, I wanted to make it work without losing it, and, well, by adding layers if needed. Okay, so we focused on that, on 108 bits of memory. We are talking about bits. We are talking about like kind of a joke sizes, joking sizes, and then we have a programmer and security. On top we have the gatekeeper, and this part on top allows us to control access to recording that memory. And then, if you don't know the sequence or the secrets, well, if you don't know how you program it, you just cannot do it, no matter how much you try it. It is very unlikely that you can do it. So how do you resolve this jigsaw puzzle? Well, yes, ours again. This is a simulation after the reverse engineering. There are thousands of transistors interconnected. I could show you this very briefly. Okay, give me a sec. Well, this is what you have to build, and this is what I end up doing. I reconstructed everything, and this led me to take each component, understand it, analyze it, reconstruct it, and validating it electrically. Oh, this is a memory registry, or this is an XOR. Some of them were so complicated. This is a memory registry, and I didn't have any background in electrical engineering, so it was a bit of a demon. So at the end, I ended up with something like that, something that finally works. It took me 6 months or more altogether. What else? Memory. Memory, perfect. I managed to, well, to understand how this was written and also when it worked, because this is a black box. Anything that you simulate in simulation, well, in simulation it works, but in real world, well, you don't know what you need to happen for it to work. For instance, timings, frequencies, etc. Memory. 108 bits, as I mentioned before. Serial entry. It was programmed in series, bit by bit. Then parallel exit to all the components, line by line. So this is the configuration, 72 bits for deciphering keys, 16 bits for the range of memory to be deciphered, and 20 bits working memory. So where do I know what to write and where? Well, only by tracing it, thread by thread, cable by cable, identifying them from 1 to 108, where they go, studying these areas where they go to understand what they do, what blocks, what keys, what cryptographs go where. Well, lots of studying. And at the end, I understood, I could see how it works. And then, well, that's it. So we had 4 sequences. First one where we had signal configuration, a previous signal configuration before doing the recording. Then we have a secret key. Then we have another secret key of 20 bits. And then another secret key. So if you do not insert the signals as such, it doesn't work. It doesn't even listen to you. You analyze every component. So signals should be configured in that way, otherwise they wouldn't work. The next one, 3 touches of watch in one of the legs. So this is an Z80. So in between the legs, what we did was just to put it to sleep. Once dead or asleep, and then considering that other things were also connected to it, Kabuki listened to us. And then we gave it 3 pulses of watch. Kabuki continues to listen. It is controlled by 3 registers that keep 3 bits. Bam, bam, bam. Then I open the next sequence, next step. And the next step is very twisted. So 20 memory registers connected with 20 XNORs and then with physical obfuscation. At the end of the day, that means that we have a memory registry, you accept it, then on the right we have an XOR, accept it, and this is this electrical simulation, the reconstruction of XOR with all the layers. It works, input, output. And physical obfuscation means that one of the legs in an XOR was directly connected to one of the electrical circuits. Okay, if I show you before, okay, we have 2 levels. Here we have the 5 and then the mass below. And then the designers in the latest visible layer, interconnecting layer, they had connected the XNOR, which is the contrary of XOR. So what they achieved with that is to do hard coding of a key of 20 bits. If you do not reach this level, if you do not understand the design, if you do not understand that this is what they looked for, you will not understand it at all. And I knew that I couldn't even talk to it. I knew that I had those 3 knocks. I had to enter a counter key of 20 bits, making these XNORs to have exits, and then once I achieved that, this is the counter key that you introduce. In each bit, 1 touch of hit of watch in each leg, and if this was not enough for the Japanese, more 10 hits of watch, which is another key in one of the legs. So these are the memory registry with more XNOR, with another key, okay, 10-bit key. Well, games were difficult, isn't it? Well, the inside was also difficult. Okay, after we go over all these phases, now, yes, we do recording. Record 108 bits, and what's in those bits, and how are they ordered? So, as I said, I traced the relation of the memory, and then when I achieved all that, luckily, I didn't break the ciphering of it. It had been done before. The keys were mathematical keys, recognized keys, and then from the address key to the source key, all these pieces are in MAME in all the games, so I had to play and understand where they were each of them located and in what order. And MAME didn't mind because they do not do any CPU simulation or anything like that, or at least at this level. And last, how do we do the validation? How do we know that this works? Well, you have to build your own hardware. We are talking about hardware. All the errors and all the trials have to go through you directly through hardware. So I ended up building a programmer for this kabuki. If I am honest, for a month I couldn't make any progress. I was just stagnant because there was an inverse connection in a place that is well, a different place to where you find the programmer. I would like to finish on here. This is where the programmer is, where we have all this logic. And as I say, I spent lots of months working on that. I thought everything was there. For a month, I realized, 1 month later, I realized that they have inserted a signal here. This is what you can see. They have inserted a signal here, this leg, which is inverting something that later on, that then is connected somewhere else. I decided to take like 20 steps back and then to go back to it, and then when I did so, it worked out. So the process is wonderful. I learned a lot. If you manage to make it to the end, and if you are successful, you know this is the great satisfaction. Well, this is all from me. If you have any questions, I will be very happy to take them.
I'm putting you in a bind. Do you want to give us next year a Harvard workshop? Are you ready for it? Raise your hands, please. Thank you. You're such good-looking people. I agree with you. I agree with you. Of course, it's a very good idea because I'm 100% sure that you might have some trouble understanding some of the things done with this presentation. I spent 1 year of my life in studying this research, tracing things, tracking things out, recreation and magic. Of course, I will be much more than delighted to conduct a workshop next year with all this work and all you have now in captures, pictures and diagrams. Crazy question. If I had a 3D printer that can print out polymaterial layers of materials, can I lift up all circuit by printing by layers? Is this industry goes much advanced than the 3D. So within this chip, I don't remember how many transistors do you have inside. Kharkov added this or UBD for this purpose. As of today, I think it's impossible unless you make it in a big scale. This is crazy. Only tracing all of these signals, there are so many kilometers inside. Should you have any questions, please raise your hands. We will kindly answer back. Very firstly, my congratulations, man. It's the biggest hobby, the toughest hobby I've ever seen in so much. That's why I set up my own company, because I'm a sadomasochist person. A question for you, man. For big companies, really international big companies, powerful international companies, Intel for instance, Intel. That do they get it profits from doing inverse engineering from the competition, given so much where and there are no software specifically for automatically doing so? It's a very good question. In the light of what I publish, I'm now involved in a second project. So I got to get connected with people outside doing this for many years. There are around 20 people on the IRC channel, all of them working for big companies. Talking with this and by understanding this world much better, they do so because the espionage at an industrial level, for instance, in China, they take this thing, they modify it, they copy it, paste it, and they reproduce it fakely. And many Chinese are doing this fake espionage. It's profitable, but the last thing for all these techniques is to failure analysis. When you design something like this, you don't only design the logistic and the logic. This is done 100% on computing thing. You only have to design the manufacturing processes, which is trial and error, and industry has been doing so for decades now. So things are trial, tested, and validated, and they are inspected because they have failed. So big machines, scanning, many things are used to understand where the failure took place. Inverse engineering is focused on the area of making copies and verify I'm not being copied. I'm not suffering plagiarism. So many big investors on big things, they have big amounts of lawyers and attorneys distributed for many laboratories verifying what the competition is doing on this purpose. Oh, you have to copy me. There is an intellectual property issue going on. Thank you. The fact that you all guys are here at 8 p.m. is really, really fabulous for me. I do really appreciate it. In front of you, my friend, good evening and thank you for your very impressive presentation. And brave man, you are brave man, absolutely. Is a man in the middle Z80. The physical thing nowadays would be very expensive and costful for a company. How can you see this implemented today with a ZPA? Because if there's been a failure in the design, the change in the configuration to be more immediate for the CPGA. Absolutely agree with you. I do know many more projects, and I've been checking on the internet with the ZPGA. It has spectrum simulations totally involved in these environments. CPGA. I'm not involved in this world, but I do think it's very interesting. I'm passionate for it. CPGA for those is a chip with many logical configurable with software with their own design, and is 100% automatized. It's very used for making breakers of bitcoins, for instance. This is a very interesting topic for you guys because much of the current industry on security is based upon CPGAs, which are resettable, reconfigurable, depending on the protection. I do invite you to check this, and there's so much work to do in CPGA. It's an open world. It's like having a Linux. It's a well-known world. How many more questions do you want me to leave pass through you? 3, 4 more questions. I wind up. I'm taking a lot of time from this. I have a question for you. Sorry. My question is, did you get the ciphering password back on the original plate or card? This reprogrammer got it. I manufactured 20 units for people interested in this hobby I mentioned. Now it's widespread. I'm now involved in breaking CPR1 and carton system 1 and the 2.1. And I'm running out of time, but we are working on other similar projects. The thing is to widespread, to extend this machine, which is open source software, and you can use it for free, of course. Do you sell it on eBay? Do you sell this on eBay? Because I saw that it's something very well for. I didn't understand the question. Did you sell this on eBay? Because there are many people looking for a way to revive, to bring back to life all these Carcom plates, the CPR2. Nowadays, I have all the chips from CP2 now open, and they're waiting for them to be scanned on a microscope. From then on, a new open world is for all of you is Z plate for all the Carcoms plate system 1. What happens? What can you discover? The type of process is different. The state of the art and the configuration and the scheme vary. There is educational work behind. We're working on it, and there's still the processing of layers phase led further wise. But later on, I will show you the CPU. It's not the CPU. It's a different thing. Very firstly, my congratulations for your marvelous patience to all of us. My question links with the fact that what you have explained to us can be applied to a current technology, because you said even though Intel chip has billions and billions of chipsets, this technology is from the early 80s and the late 80s. What can we find here when we find this analysis not being crazy? The most important point, and sometimes we have seen attacks, I always double check everything. The CPUs are the most complex systems with microcode today, which is updated externally. There is still a world to be discovered of chips. If we understand the obfuscated mechanisms by the new codes uploaded on the CPU, the vector is on that way. The vector of going downstairs with billions of transistors and microscope, electronical. I will forget this. I don't do it anymore. Okay, my congratulations for your wonderful, very impressive job. I don't want you to answer my question, but there is a person in this room that from when you are 40 years, there is a person who said you cannot make inverse engineering when you are 40 years old. My gosh. I wanted you to answer me back in private. When did you start doing this job? I'm 37, so I didn't reach the age of 40 years. So I will have to get the reason, the benefit of the reason to Roman. Have you ever thought about mounting or setting a crowd effort where you have done the photographies, you upload the schemes to a collaborational area, and other people, and then you can audit and recompile the whole thing? Good question. This now exists. It's called Exopron. John McMaster pays for this project. He's one of the most biggest gurus on these issues. I've been working with him over the last years. I will be connected with him. Furthermore, publicly it's been scanned. You have a project which is almost dead. It's visual. CPU on virtual on visual. They even define the software Motorola. The secret resides on the fact that all the amateur people working on it, I don't include myself on it, they work on that industry. They don't want their names exposed to the public, to the audience, because it's not very well seen. So within the security world, no, you can be affected. Don't push the limits. So that the jobs outside the protection of rights are published on silicon PROM with a big library of CPUs from only for the first layer. The full metal, the processing is not available. I have my own ideas on processing regarding this project. They are not in silicon PROM, and I have trouble publishing with. I have to add that I mentioned before that every process of integration of CPUs is different. Every family, 150 to 100 megameters. The state of the art is different. Every design of every team designing this does things their own way. So we have to make many tips personally to get a good knack of the intuition going through. So all these pictures of the processing of multiple layers are not available on the internet. The standards are available and the mega files are available. These are the logical units, but there are so many manufacturers involved and there are different designs. So I do think I would be delighted to conduct this workshop next year and get focused on and get to the point of what's going on here. Any more questions, please? Javi, my colleague, asked me if all these schemes, Arduino scheme, are you going to publish the Arduino schemes for the programmer? Are you going to publish them? These Arduinos, I will be sending them to the arcade world colleagues, and my promise is I will publish the code. The code is very simple. What you have seen on screen is the implementation of the Arduino's code with the, I don't know if I'm saying correctly, the speaker says. You have to implement these legs. Of course, I will publish this code for you guys, for you to see what the process is about. Thank you for your attendance.